Alright, so in this video I'm going to be explaining another important article now about domain generalization, which our target is unseen during training. The title of this article is Weighted Risk Invariance for Density-Aware Domain Generalization, which uses this article in 2021 out of distribution generalization. Learning how to generalize training performance to unseen test distributions is essential to building robust, practically useful models. To this end, many recent studies focus on learning invariant features from multiple domains. However, we observed that the performance of existing invariant learning methods can degrade under the covariate shift. To address this problem, we focus on finding invariant predictors from multiple potentially shifted invariant feature distributions. So they propose this weighted risk invariance, and they show that the solution to this problem provably achieves out of distribution generalization. They also introduced an algorithm to practically solve the WRI that learns the density of invariant features and model parameters simultaneously. So these are three contributions. We introduce a novel invariant learning that utilizes weighted risk invariance to tackle covariate shift. They propose algorithm to empirically solve, which involves learning model parameters and density of the invariant feature distribution. And they use it using this alternating minimization, which is very important in optimization. Then they verify the efficacy of our approach with experiments on simulated and real-world data. Then they find out that under covariate shift in the invariant features, their method outperforms state-of-the-art baselines on benchmarks like colored MNIST and domain bed. So you see the setup in the above that, and on the bottom you see the trained predictors for our linear causal model. So for loss L, we can define this statistical risk of predictor F over an environment E. So our environment is E. For example, here we have three environments, train, and then test. So its empirical version of the risk is this equation, and empirical risk aims to minimize the average the average loss over all training samples. So this is the empirical risk minimization. Unfortunately, ERM fails to capture distribution shifts across training environments, and so can fail catastrophically depending on how those distribution shifts extend to the test data. So we assume that X contains both causal or invariant and spurious components, such that there exists a deterministic mechanism to predict the label from invariant components. So the observed features are a function of the invariant and spurious components, which we assume is injective, so that there exists G that recovers these spurious and invariant features almost surely. So we see it as a causal graph, that the environment E is dashed to emphasize it takes on the unobserved value at test time. So it affects both invariant features and the spurious features. We say that the predictor is a spurious feed over a set of environments if their value is the same for all environments. The spurious phi predictor that performs best in all environment is optimally invariant predictor, which we call invariant predictor. Causal predictors assume that there exist features such that the mechanism that generates the target variable is invariant under distribution shift. This leads to conditional distribution being invariant across domains, across environments. Then we define this is a different from risk. This is a weighted risk between two environments. So weighted risk invariance between two environments means that their risk is equal, and weighted risk invariance over a set of more than two environments means that the weighted risk invariance holds for all pairwise combinations of environments in the set. So if a predictor is a spurious phi, then a weighted risk invariance holds over epsilon for E prime. So we have a data generating process for training environment I, for example, where epsilon is just a normal variable with means 0 and sigma. And similarly, eta is a normal variable with mean and covariance. Then we can simulate, we can generate data which is, this is a spurious and this is our y. So consider a regression problem. Let epsilon E prime be a set of environments that satisfy general position. A linear regression that satisfies weighted risk invariance with respect to the loss must satisfy the spurious part should be 0. So in order to learn an invariant predictor, we therefore propose to learn FWRI that combines generalizability with good performance. The first term, so this is the first term. The first term enforces ERM, so this is ERM. The second term enforces the weighted risk invariance. This is the weighted risk invariance. And the hyperparameter lambda controls the weight of the WRI regularization. So you see you can plot the graph between invariance features and the spurious. So you will see how they are related to each other. And even as the number of samples increases, these methods continue to select spurious classifiers, while the WRI method quickly converges to an invariant. So WRI, the red one, you see that it quickly converges to invariant classifier. And they compare it with IRM, which searches for optimal predicted unlatent space. To make the dependence of weighted risk on invariant feature densities explicit, we write the associated densities as a parameter of weighted risk. And beta here is a hyperparameter. So these are the limitations of their method. So they demonstrated that WRI predictor outperforms state-of-the-art baseline in the covariate shift in invariant features.